So the purpose of this lab was to utilize a bar magnet in order to measure the distance dependence of magnetic fields due to permanent dipole moments, and in turn compare that value against the predicted distance dependence as computed by the Biot-Savart law. Some of the fundamental principles explored throughout this lab were the Biot-Savart law for magnetic dipoles off-axis specifically. You can see the formula here. We have the Biot-Savart law for the on-axis B field of our magnetic bar, which is going to be our system right here. We have the distance dependence formula to relate the magnitude of the bar to distance and our factor n. We have our linearization of distance dependence in our graph, and we'll get to that later. Some example of our final results is n equals negative 3.05, and our mu, or our magnetic dipole moment, was 2.406 Newton meters per Tesla. So the initial conditions was our system was the magnetic bar, our surroundings were the magnetometer, gravity due to Earth, and external electric devices. We needed to determine magnetic north first, so that was taking into account the magnetic field of Earth. We need to next locate the magnetometer chip on the phone, and to do that you place the phone perpendicularly to the magnet a distance away along the meter stick, and you move the phone perpendicularly to find the max of our b of x value and the min of our b of y value, and then you rotate the phone vertically 90 degrees, and you repeat the same step, but you find the min of bx and the max of by. So once you have your magnetometer location, our procedure is we're going to want to find the distance from the magnet to the sensor where the magnitude of our b of x value is 20 microteslas, and record it 3 times, and you're going to repeat that up to 220 microteslas. Then you're going to determine a distance d perp from the bar where b net is equal to 100 microteslas. You're going to record the value of the magnitude of by where the total magnitude b net is equal to 100 microteslas. Then you're going to add a second meter stick perpendicular to the first one at the magnetometer. Move the phone up and along the second ruler a distance d perp from step 3, which you were finding there. And then you're going to record the bx, y, and z at this location. And you can see my sample observations here. Then you're going to want to subtract by of Earth from by measured to account for Earth's magnetic field, and repeat 3 times. So you can see here in our data that the linearization of our graph is here, where we have ln of k is equal to negative 14.547. Our n factor is going to be right here in our formula, so it's negative 3.0529, and we have our x and our y as well. And I found that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and n is negative because the b field will decrease as distance increases. So to calculate mu, I first knew that we could set the magnitude of the bar equal to kr to the n as our distance dependence, and I also know that on-axis b field for a bar magnet was equal to mu 0 over 4 pi times 2 mu over r cubed. I set those equal and I solve for mu, and then we find k and n from our linearization formula on our graph, and we plug those in to get a total of 2.405 Newton meters per Tesla. So in my coding, we have our constant set here. We use our mu mag, which we just calculated in the previous slide, and we defined our dipole moment function right here for a B field off axis. This is us initializing our observation locations and then actually getting the arrows for the magnetic fields at those observation locations. Finally, we needed the magnetic field for our off-axis observation location, so we used our d perp average distance, and we got our magnetic field at that location. And you can see some of the final results is that our calculated B net was 3.144 times 10 to the negative 5th Teslas, while our observed V net was 5.91 times 10 to the negative 5th Teslas. This was a 53% difference between our observed and calculated magnitudes, but at least they were the same magnitude of 10 to the negative 5th, so they were similar. And that proves the Biot-Savart law. So what if we hadn't oriented our experiment to compensate for magnetic orth and had instead laid out our meter stick at some intermediate angle? Our magnetic field calculation would be even less accurate, as the b of x on the magnometer would be off for all observations. This is because these observations would be affected by Earth's magnetic field and the magnet wouldn't be pointing true north. So what if we were to stick two identical magnets together end to end and run the experiment again? The magnetic field's magnitude would essentially double due to the superposition of magnetic fields. The magnet would still be treated as one larger magnet with a different dipole moment due to different separation distance, and our distance from the magnet to magnetometer would be less for all of our RLX values. Some errors where we didn't mark the location of the magnetometer correctly, the distances at which magnetometer readings were taken may not have been exact, and electric devices and materials in the vicinity could have thwarted readings. Finally, our computational model could not have taken into account the impact due to Earth's magnetic field, and it's assuming perfect conditions. Thank you.